next bit here, Zach, should be review, because I believe Morrison does some of this. So this is, just so we're clear, classical gravitation, as Ashton keeps muttering under his breath, a lie, for reasons that general relativity makes totally obvious. And just because there's a classical explanation for something doesn't mean that the classical explanation is the best explanation. Classical physics does a lot of things really, really well. In the reference frame that is our planet, Newton had a whole bunch of really good ideas, and they all worked. The only problem is when things get really big, really small, or really fast, or really cold, or really hot, classical physics breaks down entirely. And so there must be better physics going on in the universe that explains a wider range of situations. It doesn't work. General relativity says, I'll say no gravity. And for those of you who are just watching this video, oh, I am frozen. Hold on. Why am I frozen? That looks dumb. Do that. Do that. Do that. Oh, see, not frozen anymore. For those of you who are just watching this video, I will post a link to the YouTube video that does a better job explaining general relativity than I can. Okay, classical gravitation. You've seen it before, universal gravity. We say that gravity is a force, it's not a force, that exists between the Earth and the masses on its surface. This is a lie. But we're going to go with it because it works. In fact, gravity is universal. It exists between any two masses in the universe. So what this says, if we're going to compare it to what general relativity says, is that massive objects curve space-time. That means any object that has mass at all will curve space-time. The measurement of the curvature, though, because it's dependent on the mass, is going to be so small from you guys, which you've seen. You guys have used the equation that we're going to look at here in a second, to the universal gravitation equation to measure your gravitational pull with someone else. You did this last year, Physics 11? Okay? So that means, in fact, that no, you're not creating a gravitational pull on someone else. What you're, in fact, doing is warping space-time as well, slightly, for that person. So the gravity below shows two masses, m and m. Big M is the greater mass. Little m is obviously smaller mass because it's little m. The force of the gravity, compare the gravitational forces on these two masses. Gravitational forces on those two masses needs to be what? The same. Who said that? Santander, was that you or is that Animal? Animal. It's the same. So what you're saying is that Fg this way, the gravitational pull of the little mass on the big mass, has to be equal to and opposite this guy. That's Newton's third law. Every action has an equal and opposite reaction. So if big M is pulling with red Fg, then little m has to be pulling with blue Fg, and these guys have to be equal because every action has an equal and opposite reaction. Now, I don't know if you looked at the experiment done by Henry Cavendish and others since him. They designed a couple really ingenious experiments to measure this small force of attraction between masses. What they found was that the force varied directly with each of the masses and inversely with the square of the center to center distances. What that means is this. Universal gravitation, the force of gravity between two objects, which doesn't exist, is given to us by this equation. Big G times m1, m2 over r squared. Hands up if you did not see this, if you've not seen this before. There's no shame in admitting this. I just need to know. So you all did this last year. Love it. So we can just blast through this real quick. So then the question always is, well, what is that big G? Really easy way to find big G is to do what? Math. Yes, we're going to do math, and we're going to do math with values for variables that are quite nice. So if I want to find big G, all I've got to do is look at the situation where each mass is 1 kilogram and the distance between them is 1 meter. This was measurable. Okay? And this is how they actually found out the value for this big G term here. A 1 kilogram mass times a 1 kilogram mass divided by 1 squared is just going to give us Fg equals big G, which tells us that that force between those two masses has to be 6.67 times 10 to the negative 11. In this case, that Fg is newtons. And that's where that value, that universal gravitational constant, came from. If you don't remember what the value for big G is, it's found right here on your formula sheet. Big G equals 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Because I multiplied it by kilograms squared per meter squared, canceled out all those other things, and left me with just newtons. So if you've seen this before, I'll skip example 3, I guess, then, because we've all done this before. All I need to do is some review on this. I'll give you guys this question here. Assume the mass of the Earth is 5.98 times 10 to the 24 kilograms, and its radius is 6.38 times 10 to the 6 meters. These values are also on your formula sheet if you forget them and need them in the future. Mass of the Earth, the radius of the Earth, this is given to you in kilometers. Conversion from kilometers to meters is what? You multiply by 1,000. We want to find the force the Earth exerts on a 50 kilogram person on its surface. Go! What is the force that person, that 50 kilogram mass, experiences? If this is review, if you've seen this before, give it a shot. Starting with the universal gravitation equation. Actually, you got 489.95 newtons using the universal gravitation equation, yes?
Yeah, and it told me like,
What is...
9.8.
Yeah, the alternative, at or near the surface, we could just use Fg equals mg, where little g is... It's not actually 9.8, it's 9.8. Well, yeah, it goes on forever. Yeah. But we could have used this. I told you to use universal gravitation. If you do use this, this is going to be 50 times the value we round to is 9.8. That's 490 newtons. If you had issues with this top piece, please let me know. What But the important thing that I'm hoping you saw last year was this. There's an equivalency between this g big M over r squared and this little g right here. So what this can give you is, if we use this particular term, actually I'll just write it out like this, that little g is equal to big G M over r squared. So this is acceleration due to gravity on some planet. Doesn't have to be a planet, could be a moon, could be a space station. Where that big M is the mass of the planet. And little r here is the radius of the planet. So you could find the acceleration due to gravity anywhere in the universe, assuming you know the mass of that object and the radius of that object. Radius is a lot easier to measure than the mass, but the mass is measurable as well.
Yes.
Sorry? Well, you just flip the scale over.
The scale up the
Well, no, that's the joke in physics. Because every force has an equal and opposite reaction, so if you want to weigh the Earth, then you just flip the scale over and you stand on the back and it's weighing the Earth instead. No, the mass of the Earth, you'd look at how it interacts with the sun. And we have a pretty good estimate for the mass of the sun. Basically, these are calculated values looking at how other objects interact with each other. That's where this is coming from. Yep. Sorry? What do you mean? It is very similar. Yeah, little m, little g, yeah. Sorry, we got you, Abigail? Okay. And there was always this caveat. I'm hoping Morrison said it last year when he was teaching you guys this stuff. The caveat here, this is on or near the surface of Earth. Now, near the surface of Earth is pretty relative. Basically, anywhere on this, like if you're standing anywhere on this planet, you're basically at or near the surface of Earth. Even on the top of Everest, you are at or near the surface of Earth. If you took the Earth, shrunk it to the size of a ping pong ball, the Earth itself, shrunk to that size, would be smoother than the actual ping pong ball that you're comparing it to. Like a ping pong ball, just the way that they're manufactured, they've got those bumps and grooves in the plastic. It just has to be, it is the way it is, just with molds and plastic and how it forms and all that stuff. The Earth, shrunk to that size, would be smoother than the ping pong ball that you can manufacture of the same size. Okay? So at or near the surface of Earth is basically anywhere on Earth. But as soon as you start to enter orbit, this value is going to start to decrease. Why? Well, because this R is starting to get larger. Yep. Sorry, Joseph put his hand up.
If there are a lot of states, planets have to be smooth, like there can't be a mountain taller than a certain height because that would mess with it.
Gravity would force a certain amount of smoothness, yes. Yes. Gravity, the way objects form it, yeah, that would happen. Which is interesting because we're using a thing that doesn't exist to explain why geology is a thing. But yeah, no, there would have to be some limit to the structure of the object, yes. Oh, that I don't know that. I can't speak to that. But they're all going to be spherical, very spherical. Okay, flip page. You've seen this. We already explained this. This idea here that Fg is equal to mg. So this is your weight is equal to the mass times gravitational strength. This is something you should have seen last year. Gravitational field strength again, which doesn't exist. So down here at the bottom, little g is equal to big G, big M over r squared, which I just argued on the previous page, which you should also have seen last year. The beauty here, with so many other things that you get taught, is that it works even though it's wrong. Flip the page. Okay, so Joseph, you asked, how do you measure the mass of the Earth? Here's how you measure the mass of the Earth. Okay? This last property, the fact that little g is equal to gm over r squared, is actually how we measure the mass of the Earth. Little g is measurable. Little g comes from the force of gravity is equal to the mass of an object times the acceleration due to gravity. We could go out into the stairwell, and I used to do this with my grade 10s when kinematics used to be part of Science 10. I don't know if that was true for you guys or not. Some of you guys, depending on when you were, the curriculum changed, but kinematics used to be there. So I would take my grade 10s out, and they would do an experiment. They would drop objects in the hallway using something called ticker tape. Hands up if you ever had the misfortune of working with ticker tape. It's so sad. You should have all done this in grade 11. Okay, ticker tape is one of those things. It's tape. You feed it through a machine. The machine goes, and then an object falls, pulls the tape through the thing, and a bunch of little dots, and you analyze the dots by measuring. It's an awful experience. Okay, ticker tape is an awful thing to work with, but it's super useful. And you can use ticker tape to find the acceleration of a falling object. Assuming you put the ticker tape machine upwards and you attach the ticker tape to a falling object, you let it go and it drops. You can graph it. When you graph the velocity changing over time, my grade 10s used to do this, you do it well, you can find that the acceleration of a falling object at or near the surface of Earth is 9.8 meters per second squared. I had once in my 8 years of teaching Science 10 did I have a student actually hit 9.8. But that's because usually the grade 10s don't know how to measure properly. I had 2 girls and they did it. It was amazing. So that's easy, relatively easy to do. A falling object, if you want to increase your accuracy, you would use a set of laser photo gates. You don't have to use a stupid ticker tape machine, but that's doable. We know that little g is 9.81 meters per second squared. Okay, easy to find. Drop an object, watch how it falls. Done. Okay. Using the experiment conducted by Henry Cavendish, we found the universal gravitational constant to be 6.67 times 10 to the negative 11. Using pretty simple geometry, we know that the Earth is spherical and has a radius of 6.38 times 10 to the 6 meters squared. Ancient Greek mathematicians did this, and they were only out by I want to say they were out by a couple hundred kilometers. It's pretty good. Using wells. Hundreds of... Sorry?
They didn't know the other side.
Yeah.
Yes, they did. The Greeks didn't, the Chinese did.
Oh.
And they're talking. They knew the Earth was a sphere. There was no debate about the sphere. There was no debate about the spherical nature of the Earth. No, it was added to history books later. Ancient Chinese mathematicians, all you have to do is go to White Rock and you can do the same experiment they did. Oh, look, there's a mast. Oh, look, a little while later, the ship rose out of the ocean. How does that make sense? Ships don't rise out of the ocean. You ever been on a boat? The only logical explanation is that it's curved as you go further, and therefore you're not seeing the entirety of the ship because it's coming up the curvature. There was no doubt in ancient mathematicians and ancient scientists' mind that we lived on a sphere. It was obvious. This came later. This bullshit about flat Earth crap came later. Okay? Sorry, I'm passionate about this. And what I'm passionate about is fighting active misinformation. Okay? So, and this is relatively easy to do. If you knew circle geometry, which unfortunately you don't because they don't teach circle geometry in math anymore, basically what they did was they had a well and another well, different places on the same planet, couple hundred kilometers, even actually it was further apart. And as the sun travels over top at the equator, eventually you're going to have the sun straight down. But when it's straight down over here, what's going to happen over here? Give me some shadow, right? Because the sun's going this way. By measuring the distance between these things on a spherical surface, they were able to calculate that we know these things are a certain distance apart. We know the shadow. We know the angle the sun's making here. They measured the curvature of the Earth within, like I said, a couple hundred kilometers. It's pretty good. We've done a better job now that we can go to space. 6.38 times 10 to the 6 meters. We square that. What does the mass of our planet have to be? Well, the mass of our planet then has to be what? Find it. We didn't take the scale and flip it down. We just did some relatively simple mathematics.
.99 times 10 to the power of 24.
And the problem, why is this not exactly 5.98 times, well, not exactly. Well, this is our limiter here. This is not the exact value for the acceleration due to gravity at or near the surface of Earth. It's actually slightly smaller than this. It's 9.805 something. I think this goes on forever. If this was if we used a more accurate version of this, we'd get a more accurate version of this. But there it is. There's the mass of the Earth, Joseph. It is. And there's all sorts of crazy implications there. Things like, well, if we know what the Earth is made of, if we think we know what the Earth is made of, the amount, the density of the Earth has to, reflect this mass. And so how do we know the Earth is a giant iron core? Well, things like that. Okay. So the only thing that's going to change here is we can now start to use gravity, Fg, universal gravity, Fg equals big G mm over r squared, for objects that aren't perfectly in a level plane. That's what you would have done with it last year. This year we can do stuff like this. I've got a satellite orbiting Earth. What is the net gravitational force for a satellite in orbit? Well, that's probably what you did last year, which is good, not great, because we've got a fairly massive object at the center of our solar system that's also going to be impacting this satellite as it orbits our planet. It's going to be impacting it differently at every stage along the way. But if you want to keep a satellite in orbit, you need to know how. So let's figure out the net gravitational force on this object. How do I do that? Sorry? One equation plus another equation. Can we add the equations that nicely? Why not? Well, each equation represents what? Fg equals gmm over r squared. That's a force. A force is what? Is a vector. So can you just add those equations nicely? No, how are we going to have to add them together? We can use components, or we can use tip to tail. We can do them graphically, or we can do components. Okay? So, this satellite here has a force of gravity acting that way, and it has a force of gravity acting this way. I'm going to call that Fg Sun, and this guy over here is going to be Fg Earth. Let's find out what those values are, shall we? Fg Earth. G, M big E. We'll call this little m sat. Love my subscripts. Over r squared. Now, We look at the information given to us for our calculation. Big G is 6.67 times 10 to the negative 11. I'm just going to go fast here because you guys have seen all this before. 5.98 times 10 to the 24. We're told that the mass of the satellite is 30,000. The radius, this r, just a bit of a review, is the distance from what part of the Earth to the satellite? The center of the Earth to the satellite. Okay? So this thing tells us that center to center distance is 200,000 kilometers. We're just going to add 3 zeros to it to make that meters. 200,000 kilometers becomes 200 million meters. Make sure we square that. You're going to find that the force of gravity from the Earth on that satellite is 299.15 newtons if you were to run that yourself. Equivalently, the force of gravity from the Sun is equal to 6.67 times 10 to the negative 11. The mass of the Sun is also on your formula sheet. It's 1.98 times 10 to the 30 kilograms, large object. The satellite still weighs the same. Sorry, ooh, bad. Still has the same mass. And they tell us that the distance from the center of the satellite to the center of the Sun is 150 million kilometers. So it's 150 and then 6 zeros to give you kilometers. Add 3 more zeros to give you 150 billion meters. It's a short walk.
I do that every morning.
Okay.
That's a long beach.
That tells us that the force of gravity from the Sun on our satellite is a surprisingly large number. For as far as it is away, the force of gravity on the satellite from the Sun is 176.1 newtons. That's larger than half the value from the Earth, which is not insignificant. If you're trying to put an object in orbit, you've got to consider what's going on out there. So now we don't want to find those things. What we want to find is the net gravitational force on our satellite. We're going to make the triangle. Okay, so FG Earth is this way. Actually, we're going to do this. Make it longer. Because it needs to be, 299.15 newtons long. Which is basically 300. So this one, 176.1, needs to be just bigger than half the length of this one. When you're drawing these things, thinking about it that way is important. So let's say that that's just larger than half. This is going to be FG net. This orange one is 176. I should have used green. I don't know why I changed the color, but I did, so we'll deal. We need an angle. What's the angle? 45 is where? 45 is in the top left. So if I did this, you're telling me that this would be 45. You're right. That angle there is 45. Because if I go back to my base of my blue one, that angle there, the big one, from the blue one to my, we can't go north, south, east, west in space. But my XY coordinate grid in space still doesn't make sense because it's what's up in space. But that's okay. We'll deal with it. That angle there is 45, so that angle there has to be 45. This 176.1 is flat, straight towards the sun. So this is 180 degrees. 180 minus 45 is 135 degrees in here. And now I can use cosine law. F net is going to equal FG net is going to equal the square root of the following expression, 176.1 squared plus 299.15 squared minus 2 times 299.15 times 176.1 times the cosine of 135. You're going to find that FG net is going to equal 441.6 newtons when the satellite is located right there. So what that tells us is when the satellite is whipping around this portion of the Earth, it's going to theoretically speed up. Now we got to find the direction because force is a vector. We can use sine law. Absolutely, sine law is going to give us this angle right here is the angle I'm going to find using sine law, because I know this big black one is 45. So if I can find this little red one here, 45 minus this one is going to give us this little blue one here. And that little blue one there is going to be the angle that we need. So sine of theta over the side that's opposite, 176.1, is going to equal the sine of 135 over this 441.6 newtons here. If you do that, you're going to find that that angle is 28.6 degrees, and because there's no such thing as north, south, east, and west in space, we're going to say that this thing, according to our picture, is above the horizontal. Sorry? Oh, right. That's, yeah, 45 minus this. Thank you. 28.6 degrees, which means theta actually has to be what? Let's go fix that. I'm jumping ahead here. Sine of 135 divided by 441.6 times 176.1 equals sine inverse. Answer equals. Theta's at, yeah, you're right. Sorry guys. Theta is 16.38 degrees. 45 minus the answer is 28.62. There it is. Sorry, my apologies. Good catch. Are we cool with this, or would anyone want me to go back and I can tweak this really easy to show you components? Does anyone rather see component method for this? Okay. Component method, I'm going to scroll this up at the top here. All I need are these values down here. So the component method is going to look like this. I calculated this green one already is 176.1. So the component triangle that we're using for FG Earth is just this guy here. This red one that I drew in here, I'll zoom this in. Okay. We found FG of the Earth to be 299.15. So this component right here is going to be 299.15 sine 45. And this component right here is going to be 299.15 cos 45. The beauty of sine and cos 45 is that they are the same. So this is going to be 211.53. That's going to be 211.53. Ouch. So then what you're going to get is a triangle that looks like this. These two are adding because they're acting in the same direction. So you're going to get something that looks like that, where this distance here is 176.1 plus 211.53. That's 387.63. Thank you. And that is 211.53. FG net is that way. So using components, we could make this triangle instead. The value is going to be the same, and you use tan to find that angle. Doesn't matter if you use components or graphical addition of vectors, you're going to get the same thing. Comments, questions, concerns? This, I'm willing to bet, is the extension that didn't exist last year. Okay? Dare I? Okay, I'm going to give you a couple questions out of this to practice, just a bit of a review. This is, yeah, 1, really easy, should be straight out of the stuff you did last year. 2, you should have done, no. 4 is a good one. You like 4. I want you to try 5. Ooh, mass of the moon in 6 is good. And I want you to do number 10. Oh, 9 and 10. I'll give you 9. 9 and 10. Okay? There you go. We'll give you half an hour to do this, then we'll do the next lesson. Hoping this is review. We're going to add the vector stuff into this now as well. Question 4 is the one that does this the best. Question 4 is good. Think it through.